Hi friends, welcome to our channel. Here we are going to look at problem 4016, maximum area of two non-overlapping square submatrices. So the ingredient for solving this problem actually in our video will be the following. First is dynamic programming. So this is the very typical technique. The second one will be binary search. So before we start the video, actually in our channel we have a playlist for DP and a playlist for binary search. You can check out. So now let's come back to the problem statement. So here we are given a 2D array, a binary array. So here 1 means usable and 0 means not usable. So our task is to find two submatrices that satisfy the following conditions. So the two submatrices are both square matrices and with the same set length, and also they should be non-intersecting. In other words, separate. So we want to return the maximum possible area of each of the two squares. If it's not possible to choose two such squares, we are going to return 0. So 0 will be our default one. So if you look at the three examples, in the first one, so the largest set length will be 2. For 2, you can find two non-intersecting squares. So each has area 4, 2 times 2, right? So that's the return. And for the second example, actually, you can find two submatrices or sub-square matrices. Each has set length 1, so the output will be 1. And for the third example, you cannot find two submatrices of set length 1 or the same set length. So the default return will be 0. So the constraints are the following. So first, m and n, the length and the number of rows and number of columns is bounded above by 500, right? So this is the binary matrix. So our plan will be the following. First, we need a way. To determine the possible square matrix size, the largest, right? So for this one, actually, it's a very typical problem. So this is a classic problem, I would say, classic one. So we can use dynamic programming. Well, for the another one is that we need a condition to indicate that the two submatrices or square matrices, in general, it's just the two submatrices, are non-intersecting. So I'm going to specify the second one during the coding. And the third one is how to effectively find or locate the key, right? So once you locate the key, so the return should be k squared, right? So with that said, let me firstly, for the third one, so we're going to use binary search. So I'm going to walk through the transformation and transformation procedure. So now let me first use DP to get some information about square matrix size. So DP for square matrix size. So the interpretation will be the following. So dpij will be defined as the maximal square matrix set length, also number of rows or number of columns, right? The same, ending with say bottom right at index ij. So that's our interpretation. So once I wrote like this, you should realize that I'm going to use tabulation. So first, I'm going to get the number of rows and number of columns. that's also standard, right? And then I'm going to do this times n for dummy index in range m, right? So when you do 2D arrays, you should from inner to outside. So this is the number of columns. So this is the number of rows. If you do 3-dimensionals, so you should also from inner to outside. So once we have this, so we just need to fill up the DP table. So this is rather straightforward. So for I in range m, so for j in range n, right? So if the matrix at ij equals 0, so then that value should be 0 because there's no matrix satisfied, no valid square matrices. We just use the default. If it were 1, so we distinguish two cases. One is it's in the boundary. So if it were in the boundary for the indices, so for the square matrix size, it can only be 1. And then afterwards, if it's not in the boundary, it means that we can consider I-1 and j-1. So actually the recursion relation will be the following. So the key thing is that if we can extend the length by 1 by adding the, so for example, this is the ij, so you need to consider this column and this row and also this matrix. So it will be 1 plus min dp I-1 j, the size ending at I-1 j. In other words, in the up, right? So then dp I j minus 1 to the left, and then the diagonal direction, right? So the minimum of the 3 plus 1 will be the size if you can extend, right? So this way we get this information. So if you print out this dp, so you will see for this you will get 1, 1, 1. This is 2, this is the 1, something like this. So deep, let me see, dp. So when let me see here. So here I write it wrong. It should be 1, right? Let me run. So this should be 1, 1, 1, 0. So 1, 1, 1, 0. This should be 1, 2, 2, 1, 1, 2, 2, 1, and this should be 0, 0, 1, 2, right? So here you can see you have 2, this 2, and also this 2. That's the 2 part. And then the next thing is that we want to do binary search to find the key. Binary search to find the max square matrix size such that we have 2 square matrix. Of size k, and they are separated. So this is also a part of the binary search. That is, we have 2 steps. One is define a Boolean function to yield order or monotonicity, and then we do search arrange shrinkage. So let me first define the Boolean function. So see, we can have 2 size key submatrices. So then what we want to do is that we want to make sure they are separated, right? So this way, what we are going to do, we set min I, min j to be the max, let's see, this max size. So the same. Or you can use the float infinity, something like this. This is the same, right? This is the I'm going to use this min to monitor the bottom right indices of one square matrix. And then I'm going to use max I, max j. Let's see, original set to be -1 to monitor the another square matrix, the size, right? So the separation condition will be the following actually. Let me first write and then we specify. So for I in range M, for j in range n, right? Then if dpij is greater than or equal to k, it means that ending at this indices, we can get a submatrix, a square matrix with size at least k. In particular, we have a k. So in this case, we update this mean, mean I, mean j, to be mean. The mean I is previous state and the current I. Mean j, the previous state. So similarly, we maximize I, max j, to be max, max I and I, and max j and j. So the separation condition is the following. So if max I minus min I is greater than or equal to k, in other words, it horizontally it at least k away, or vertically, because the direction can actually symmetric, right? So that's, if you have the first part, you should have the second part. Maximum j minus min j should be greater than or equal to k. So this is the separation condition. If this is the case, so we return true. So here actually from this condition itself, as long as these two conditions holds, it means max ij and min ij are corresponding to at least two square matrices. Therefore, we can have at least two. So if after the for loops you have nothing returned, so we're going to return false. Right. So that's the Boolean function. This part. So now let's look at the search range shrinkage. So let me initialize a result variable. So this will be the default return. So then what I'm going to do is this. So low and high. The lowest possible k will be 0, right? You have no valid ones. And the maximum will be max, will be mean of mn, because this is the largest possible. Then I'm going to do the search range shrinkage. So while low is less than high, then we're going to do mid. I'm going to write like this: high minus low over 2 interdivision. So in this case, so we check if we can find two square matrices of size mid. If we can, so we can set result to be mid, and then the mid is true, right? So at least we can have this. So we get this. Otherwise, so mid is high. In other words, mid is too large. So we can have high equals mid minus 1. So after this while loop, actually you will either find 0. So if you have 0, nothing make this can true. So you just return 0. If other case, we will have low and high coincide. So the result square will be the area. So result square. So that will be our full solution. Let me first run it. Let's see what's the problem. So here, let me write it like this: low equals mid, result equals low. So here, let's see for ig. So here I can do from up to high, because so this way name L, so here I would say hello. Yeah, so because this problem is find the maximum. If you do min, you can do from lower to upper, but in principle some cases if you do from low plus, it would also be good. But in this case, if low is 0, so always false, right? So that's the difference for this problem. So here I'm going to write hi. So, and then let's look at the generic case. Yeah, it passes all the cases. So here, let me give a quick summary. So the first thing I want you to pay special attention is this condition. Here I'm writing low is less than high. Some people prefer to write low is less than or equal to high. So you need to adjust this. So this is the boundary. And here is a shrinkage direction, because here we want to find the maximum one. So we from the large to small. If you want to find the minimal one, typically if you from small and then increment, that will be always in your favor. So that's one thing. Another thing is that in this problem, what we want to return is the set square, right? Just pay attention to the problem statement. Actually, for using binary search, there are some very delicate points. So I would refer you to our binary search playlist to look at more problems, look and practice more, right? So this is the about this. Here, I also want to point out this part. So the way we find at least two square matrices with sets key, it's actually due to this condition, right? And existence and then separation. Another one is that as a prerequisite or as a problem of independent interest, given the binary matrix, how do we find the largest square matrices with all ones? So this is one. Another problem is that given the binary matrix, how do you find the largest, say, rectangular matrix? That's also a extension problem. So with that said, I guess that's it for the current video. Thank you for watching.